Calculus 1 video lecture number 14 on rates of change in the natural and social sciences. So now that we have the tools to calculate most derivatives, let's see how to apply them in the natural and social sciences. And so first example, we're going to go back to particle motion, which we've discussed before, but now we can answer a lot more interesting questions about this little particle. Here we go. A particle moves according to the law of motion, S equals f of t, t greater than or equal to 0, where t is measured in seconds and s is measured in feet. So they're giving us the function, its position function, which tells us at any moment in time where it is on the s-axis. Okay, so this particle is only running in one dimension, back and forth, poor little guy. All right, part A asks, what is the velocity at time t? So we know the velocity is equal to the derivative of the position function. So v of t would equal f prime of t. So all I need to do is go ahead, differentiate this function. It's a sweet little polynomial, so we just go term by term. Derivative of t cubed is 3t squared. Derivative of the next term is going to be negative 18t plus 24. So there's the velocity at time t. They didn't ask for a specific time, so I'm just giving them the function. All right, part B asks, when is the particle at rest? So if the particle is at rest, that means it's not moving. That means the velocity should be equal to 0. So I'm going to go ahead and set v of t, my velocity function, equal to 0. So that means 3t squared minus 18t plus 24 is going to equal 0. And now we need to solve this equation. Right off the bat, let's just divide the whole thing by 3. That way it'll be simpler to work with. Divide by 3, divide by 3. And now I have here t squared minus 6t plus 8 equals 0. Okay, does this factor? Oh, it sure does. This is t minus 2 times t minus 4 equals 0. So that means the particle is at rest at t equals 2 and t equals 4 seconds. Make sure if they give you units in the problem that you include them in your answer. Okay, lovely. Let's move on to part C. So part C asks, when is the particle moving in the positive direction? So positive direction means that the velocity should be greater than 0. So what we're going to do is solve the inequality where v of t is greater than 0. Remember, v of t, we have it factored right there, is we divided by 3. I'll throw it back in there. Times t minus 2 times t minus 4. I want to know when that is greater than 0. Do you remember how to solve quadratic inequalities? If not, I'll link a video up here. Okay, you have to make a number line and test your intervals. So t starts at 0, so I'm not going to draw to negative infinity. I'm going to start my number line at 0. This is for v of t, and then you list the zeros from the quadratic equation on the number line. And then you test each interval. So say, for example, in this interval, I'm going to test with t equals 1. Okay, so this is positive. If I plug in t equals 1 here, this factor is going to be negative. This factor is going to be negative. So a negative times a negative is positive. That means velocity is positive there. Say I'm looking at the interval from 2 to 4. Let me plug in t equals 3. The first factor would be positive, the second one would be negative, so the velocity is negative here. And then if you plug in something greater than 4, say t equals 5 or 100, whatever, velocity is positive. So when is the particle moving in the positive direction? Well, let's see here. V of t is greater than 0 from 0 to 2 and from 4 to infinity. Now, do I actually include 0? Well, let's check. So v of 0, if I plug it in, is equal to 24, which is greater than 0. So we do include 0 on the interval. So I'm going to say it's moving in the positive direction from 0 up until 2. I'm not including 2 because the velocity is 0 at 2. Union 4 to infinity. Okay, good. Part D. I'll read it to you here. What is the total distance traveled during the first 6 seconds? Okay, here's what you have to understand. The total distance traveled has to be computed by looking at several subintervals. Why? Because here's what the particle's doing. From 0 to 2 seconds, it moves in the positive direction. Then from 2 to 4 seconds, it goes in the negative direction. And then from 4 to 6 seconds, it's going back in the positive direction. So it's kind of like, think about when you run a mile on a track in high school, right? If you look at your position where you are when you start, and then you look at your position where you are when you finish running the mile, you would say, oh my goodness, you went nowhere because your starting and stopping position are basically the same. So the total distance traveled must have been 0. Is that true? No, it's because you were running around and around in circles. So same thing with this particle. Because it's changing directions, we're going to have to figure out what the total distance is for each of the subintervals and then add them together. Because we don't want, when it was moving in the negative direction, for that distance to cancel out with the distance that it covered when it was moving in the positive direction. Okay? If we were in person, I'd be running back and forth in the classroom for you to get an idea. Anyways, the total distance traveled is going to be computed by taking the displacement for each of those subintervals. So I'm going to take the position at 2 seconds, subtract the position at the start of the interval, right? That's when it's moving in the positive direction. Then I'm going to add, and just put absolute value around it. I know it should be positive there, but just to be safe. The next time it changes directions was at 4 seconds. So we're going to take f of 4 minus f of 2, put absolute value on there. And then the end of the interval, they want it from 6 to 4 seconds. So f of 6 minus f of 4. Okay, and then just plug everything into the position function. And I did that already for you to save us some time. So f of 2, that's going to be 20. F of 0 was 0. F of 4 was 16. And f of 2, we have that already, is 20. And f of 6 is 36. And f of 4 is 16. So this is 20 plus positive 4, right? You change the sign there. Plus 20. So the total distance traveled is 44 feet. All right, good. Now they didn't ask for this, but I want you to see the difference between total distance traveled and the displacement. Displacement means just straight up give the change in final position at 6 seconds compared to initial position at 0 seconds. So that would be 36 minus 0, which is 36 feet. So notice what happened is the displacement underreports those 8 feet that come from here, those 4 feet when it went in the negative direction, because basically it went backwards 4 feet and then it had to cover those 4 feet again when it was moving in the positive direction. So that's why the displacement does not equal the total distance traveled. Just think when you're running the mile, right, your displacement, your change in position does not represent the total distance traveled. Okay, part E, are you ready? Part E says, what is the acceleration of the particle at time t? So remember, acceleration is the second derivative of the position function. Or you could think of it also as the derivative of the velocity function. Okay, what was the velocity function? In case you forgot, I'll rewrite it for you right here. Velocity function is 3t squared minus 18t plus 24. So just differentiate that one more time. So acceleration is equal to 6t minus 18. And the last question, I won't scroll up, I'll just remind you what it says. It says, when is the particle speeding up? And when is it slowing down? So in order to answer that question, you have to understand one basic principle, and that is the particle is speeding up when v of t and a of t have the same sign, and it's slowing down when v of t and a of t have opposite signs. So remember, acceleration gives you the rate of change of the velocity. So if the velocity is positive and the acceleration is also positive, then that means the particle, its velocity is moving in the positive direction, and it's also increasing the rate at which it's moving in that direction. Same thing if they're both negative. That means the particle is moving in the negative direction and the rate of change is also negative in that direction. If they have opposite signs, just think they're competing with one another. The particle's moving in the positive direction, but the rate of change is negative of the velocity. So when they have opposite signs, they're fighting and it's slowing the particle down. Okay, so how are we going to answer the question? Well, we're going to use that little number line that we had earlier that showed the sign of the velocity function, and then I'm going to stack the acceleration function right below it so we can compare. So from up above, here I remember it, don't worry, I'll draw it for you. We had the velocity function, remember, at 0, and then we had 2 and 4, and we listed the signs, right? So velocity was positive from 0 to 2, it was negative from 2 to 4, and then it was positive the rest of the way. So what you're going to do now is make another one for acceleration right underneath it. And you're going to list the zeros of the acceleration function on here. So what are the zeros of the acceleration function? Well, here's a of t. If it equals 0, that means 6t minus 18 is 0. So t would have to equal 3. So we've just got that one little number here, 3. And then let's check. If I plug in something smaller than 3, say 2. If I plug in 2 for t, 6 times 2, that's 12 minus 18. So acceleration's negative here. And then bigger than 3, it's going to be positive. Okay, good. So what do we do now? Well, I like to draw vertical lines through all the zeros. So draw one through 2. Draw one through both of them, okay? We got to look at the system all together. Come on, nice and straight. There we go. One there and one there. Okay. So we have 1, 2, 3, 4 little subintervals to look at. We've got this one, this one, this one, this one. So I'm going to list speeding up, slowing down, and then you tell me which one it goes in, okay? All right, so I'm looking at this first interval here, which is from 0 to 2, right? And I notice velocity in that interval is positive, but acceleration is negative. So where would the interval from 0 to 2 fall in? Is the particle speeding up there, or is it slowing down? That's right, it's slowing down because velocity and acceleration have different signs. Okay, next interval, let's look at, it's 2 to 3, right? 2 to 3. Let me scoot this down so it's not so squished. Okay, 2 to 3. So velocity is negative, acceleration is negative. They have the same sign. That means the particle is speeding up. Beautiful. Next interval is from 3 to 4. Velocity is negative, acceleration is positive. They have opposite signs. That means it's slowing down. So that's from 3 to 4. And then last interval is from 4 to infinity. And notice they both are positive. Here, positive, positive. So if they have the same sign, then that means the particle is speeding up. Ooh, it speeds up for all eternity, my goodness. And that's our answer, okay? So I think that's the cleanest way to organize the info. It's always served me well. Whoa. Just make sure you box everything nicely at the end. Oh, beautiful. There's a good answer. Okay. Let's look at some more examples with particle motion. Here we're going to talk about a particle that's moving vertically. So the height in meters of a projectile shot vertically upward from a point 3 feet above ground level with initial velocity of 40 feet per second is given by the following function. H, that's its height, equals 3 plus 40t minus 16t squared. So when you're taking physics, this is going to be one of your kinematic equations that you're going to learn. But right now, we'll just give it to you. Part A says, find the velocity after 2 seconds and 4 seconds. So first thing I need is the velocity function. I don't have it. So v of t, that's equal to h prime of t, the derivative here. So that's going to be 40 minus 32t. Now I can go ahead, find the velocity after 2 seconds and 4 seconds. So I'm going to plug that in for t. So v of 2 equals 40 minus 32 times 2. So that's 40 minus 64. That's negative 24. And then don't forget your units. Oh my goodness. So you know what? They're having a little bit of a discrepancy here. Why is this saying meters and this is saying feet? Okay, we're going to change it to feet. All right, I'm so sorry about that. Okay, yeah, because this is also in feet. Someone wished they were in the metric system. I can't blame them. Okay, so negative 24 will do feet per second. And then we need it again at 4 seconds. Okay, so v of 4, that's equal to 40 minus 32 times 4. So that's going to give us negative 88 feet per second. Okay, not too bad, right? We're starting off gently. B. When does the projectile reach its maximum height? Well, let's think about it. You're shooting this projectile vertically, right? So here's the height. Here's the time. And they're telling us it starts at 3 feet and it's going to go up, 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 up. It hits its max somewhere and then it comes back, hits the ground. This max height occurs when v of t equals 0, right? Because for a moment in time, the particle's not moving when it hits the max. It's actually changing direction. It's moving upward, upward, upward. It stops moving and then it starts going down, 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 down. So we're going to set v of t, the velocity function, equal to 0. So that means 40 minus 32t equals 0. Solve for t, so t equals 40 over 32. I can divide by 8, so that's 5 over 4 seconds. Okay. C asks, what is the maximum height? So they want to know what is the position, right? Or how high is it when t is 5/4 of a second. So I'm going to come back to the height function that they gave me at the very beginning and plug 5/4 in for t. So h of, I'm going to write it like this, h of 5/4, so you see what's going on. That's going to be 3 plus 40 times 5/4 minus 16 times 5/4 squared. Beautiful. So this is 3 plus 40 over 4, that's 10. So this is 50 minus, look, you don't need a calculator. Don't you dare grab it. 4 squared is 16. So this is going to cancel with the 16 here. And 5 squared is 25. See? 50 minus 25, that's 25 plus 3, 28 feet is the max height. There are times when a calculator is necessary, but it's not always necessary. Beautiful. All right. Part D. When does it hit the ground? So how would you figure out when it hits the ground? That would be when the height, the original function, is equal to 0. So let's go ahead and figure out what that's going to be. So I'm going to set h, my original function, equal to 0. So that means 3 plus 40t minus 16t squared equals 0. I never work with quadratic equations unless the quadratic term's positive. It's just a mess to factor or try to use the quadratic formula on otherwise, okay? So 16t squared minus 40t minus 3 is 0. Yeah, this guy will not factor, so it's quadratic formula time. So we've got t equals opposite of b plus or minus square root b squared. So that's going to be 1600 minus 4 times 16 times negative 3 all over 32. Okay, so this is going to be 40 plus or minus the square root of 1600 plus 4 times 16, that's 64 times 3, 192 over 32. All right, so we've got 40 plus or minus the square root of 1792 divided by 32. And 1792 is actually 256 times 7. So this is 256 times 7. I played around with it for a little bit. I figured out it was 64 times 28 and then kept breaking it down so I could get the largest perfect square out of there. Okay, so this is 40 plus or minus 16 rad 7 over 32. Let me straighten that guy out. And then I can divide out an 8 from everybody, can't I? So this is going to become 5. This is 4. This is 2. So we've got 5 plus or minus 2 rad 7 over 4. Now for my answer, this is time, right? Okay, as far as I know, we can't go back in time just yet. So I'm only going to report the positive t value, not the negative one. So I'm only going to report 5 plus 2 rad 7 over 4 seconds. Because t, we're assuming, has to be greater than 0. Okay, cool. I think they want one more thing from us. With what velocity does it hit the ground? So in this part D, we found when it hit the ground. I figured out the time value. Now they want to know what's the velocity. So I'm just going to plug whatever I got for t into the velocity function here. 40 minus 32t. So part E, here we go. They just want the velocity of 5 plus 2 rad 7 over 4. So the velocity function was 40 minus 32 times 5 plus 2 rad 7 over 4. Okay, if you want to clean this up, so this is going to be 8, right? So we've got 40 minus, and then if I distribute that 8, it's going to be negative 40 minus 16 rad 7. Ooh. So then these cancel. So you should have negative 16 rad 7 feet per second. Okay. And then on occasion, they might ask you to round. They didn't in this problem, but just follow whatever the directions say. If they tell you to round, usually they'll tell you how many decimal places they want in the final answer. So if they didn't say anything, I would just leave it like this. Okay, this is exact. All right. Just to give you an idea, it's negative 42.336 feet per second, just because I felt like rounding to 3. Okay, how are we doing? Let's look at one more. If a rock is thrown vertically upward from the surface of Mars with a velocity of 15 meters per second, then its height after t seconds is h equals 15t minus 1.86 t squared. So part A asks, what is the velocity of the rock after 2 seconds? So first I need the velocity function. How do I get it? Yeah, I take the derivative of the height function. So it equals h prime of t. So let's go ahead and differentiate 15t's derivative is just 15. Minus, I'm going to have 2 times 1.86 t to the first. So this is going to give me 15 minus 3.72 t. That's v of t. So now v of 2 seconds, is going to be 15 minus 3.72 times 2. And you can go ahead, use your calculator if you like. This is 7.56. What are the units? What are the units? Meters per second. All right, good. Part B. What is the velocity of the rock when its height is 25 meters on its way up and on its way down? Okay, so first of all, I don't know at what time it's at 25 meters. So here's what's going on. Here is what is going on, people. We've got this rock. We're throwing it vertically, same as before, okay? They didn't tell me an initial height. There isn't one. Say this is 25 meters right here. There's one time where it hits 25 on the way up, and then it hits 25 feet again on the way down. So there's going to be a first time when that happens and a second time when it happens. And they want the velocity at each of those times. So first thing I have to do is figure out what those times are. So I'm going to set h of t equal to 25. So that means 25 equals 15t minus 1.86 t squared. Let's set this equal to 0, so 1.86 t squared minus 15t plus 25 is 0. It is quadratic formula time if I've ever seen one. Okay, so t equals 15 plus or minus square root b squared, so negative 15 squared, that's 225 minus 4 times a times c all over 2 times 1.86. So this is 15 plus or minus the square root of 225. Well, 4 times, I was going to use the calculator, but I just feel silly now. 4 times 25 is 100. 100 times 1.86, that's 186. Over 2 times 1.86, we just did it. It's 3.72. So this is 15 plus or minus rad 39 over 3.72. So now, okay, let's go ahead. Let's get the calculator out. I won't feel embarrassed. And then 15 plus rad 39 divided by 3.72, that gives us about 5.71. And then 15 minus rad 39 over 3.72 is about 2.35. So which one's on the way up, which one's on the way down? The earlier time is on the way up, right? Because it happened first, and then afterwards that's on the way down. All right, so we got these times. This is 2.35, this is 5.71, and then remember the problem asked us what the velocity was at each of these times. Okay, so now we just have to plug them into the velocity function. So let's do on the way up. The velocity function, here I'll rewrite it here so we have it. Velocity was 15 minus 3.72 t. So on the way up, you just need v of 2.35. So that's 15 minus 3.72 times 2.35. So you should get approximately 6.26 meters per second. All right, and then on the way down, only difference is now I'm going to plug in 5.71 for t. So we've got 15 minus 3.72 times 5.71, which is approximately negative 6.24 meters per second. All right, we probably just have some rounding error because I'm pretty sure they should match up. Okay, so that concludes the lesson. I'd say the big takeaway is this is the position function. Sometimes it's called h of t, x of t, y of t, f of t, etc. You take a derivative, that's velocity. You take another derivative, which is v prime of t, and that's acceleration. And usually we don't do another one, which is jerk, that I mentioned in a previous video. These are like the three big ones we work with. Okay, great. So don't forget to give the video a thumbs up. Subscribe if you haven't already. Share it with your classmates and whoever else you think would enjoy it. And stay tuned, we've got more derivative stuff to learn. Oh yeah.